The proposed workflow of the Compact project using IoT-PML includes not only modeling of software and hardware aspects to enable software generation on various levels of abstraction, it also provides a tight integration of analysis and optimization tools. By implementing plugins for the workflow, these tools can be enabled to access and alter model information. The use case demonstrated here is the integration of tools to automate the analysis of timing and power aspects of the vehicle classifier software model. In this demonstrator, the following aspects are covered: generation of source code for the main routine out of the IoT-PML model, and modeling of design alternatives, one with manual annotation of analysis results and one with automated annotation of analysis results with a tool plugin. Now, let's dive into the model describing the application layer of the vehicle detector. This diagram depicts software components which TinyYOLO is comprised of. TinyYOLO is an object detector using neural network algorithm to get the vehicle locations and classification of the vehicle from the video frame. This diagram shows which software component is either using or implementing which interface, and the two variants of embedded implementations. First, the original one using the pink board, and the second, a board utilizing a Cortex-M0 Plus based system on chip. The goal is to benchmark the CNN application on a very low power platform. So, we modeled the software components for the CMOP variant in the design repository and created a behavior specification for the main loop using the dedicated diagram. The behavior is defined by three actions of a type call operation: receive image data, run CNN action call, and send recognition data. The run CNN action call is stereotyped as a control point which defines the point of measurement, and created NFQ duration type as a requirement linked to this control point. In this example, the NFQ is used to model a timing constraint of this specific application. The run CNN action call should be executed and finished twice per second. To achieve this, a benchmark was compiled out of the CNN model and the complexity reduced so that the code fits on the memory of a development board. Okay, let's confirm that, and now we can visualize the source code. Here is the header file, and here is the C++ file having those three actions implemented. This benchmark is then evaluated using the analysis tool plugin. First, we need to create NFQ duration type, but this time as a description. Then create start and stop traces so we clearly define the control flow of our interest, and from the context menu initiate the time analysis. Enterprise Architect passes the appropriate parameters to the analysis tool, and at the end of the process, the tool annotates back the results. The simulated execution time for this version of the benchmark was 27,402,099 cycles, which equals about 1.14 seconds when executing with a core frequency of 24 MHz. It also saves and links a detailed HTML report which can be directly opened using the context menu of an element. Here we see a list of cycle values for different instruction classes, or we can quickly navigate to the location of the NFQ by clicking on the hyperlink. In case if you don't have the mechanisms to automatically perform and annotate the analysis results back to the model, IoT-PML allows you to do it manually, as we did for the pink board implementation of the Run CNN library. And that's it. Just remember that seamless integration of the code generation, time analysis, and optimization tools enable developers to explore the impact of changes in the implementation and design of their software, model and compare the design alternatives of different implementations and algorithms directly in the model environment, and access and alter model information in a convenient way.